discuss today about chemical periodicity, uh, periodic table of elements, and we have 7 periods and 18 groups. What is so special about the periodic table, and when is the discovery of the periodic table system, and which year, and what is so special about 2019 international year? So 2019 international year is referred as periodic table of chemical elements because 1869 it is considered as periodic table system was first proposed or discovered by Mendeleev, and international year of periodic table in 2019, which commemorates 150th history of periodic table of chemical elements. And so, what is very interesting about this IYPK is the importance of periodic table of chemical elements and how it influences the achievements in modern science, reflecting the essence of chemistry, but also its impact in interdisciplinary sciences is very vital. So, Dmitry Mendeleev arranged the elements based on atomic mass, and he saw some of the repetitive patterns basing on the periodic law with respect to increasing atomic mass, where the properties are recurring, and which also tells us about with same properties in the same column, and there are a lot of unpredicted properties and undiscovered elements can be arranged across in the and where atomic mass is not did not fit the other properties, they are ordered into other sets like tellurium and iodine. And still there are some questions which are not very well evaluated in periodic table, which is where does the hydrogen belong, whether it can belong because in the first group or in the half-filled electrons in the 4A, or like nitrogen family, or in the halogen kind of family. So this is one uncertainty which is present in hydrogen position. And what exactly is periodicity? Periodicity of elements means the reoccurrence of same properties of elements at a regular intervals with increasing atomic numbers when they are arranged. You call it as periodicity. And because of the periodicity, you have similar electronic properties and outermost energy shell, valence electrons. The pattern will be recurring. What are the important trends in the periodic table we can expect? So the important trends in periodic table include the number of electron shells across the period will remain the same, whereas the shells are added down the group. And valence electrons, they increase by 1. Here, valence electrons are same down the group. Similarly, electronegativity, ionization, and energy affinity, they all increase across the period and decrease down the group. And metallic character decreases, down the group it increases, and non-metallic character increases across the period, and metallic character increases down the group. So there are a lot of advantages in the periodic table when they are arranged. You can arrange based on the atomic number, and of these elements are arranged with respect to electronic configuration, and periodic properties show a gradual variation across different intervals, and it is easier to reproduce or understand the points. So the important points are, what are the loopholes is the demerits or the disadvantages of this arrangement of things in the periodic table. The hydrogen position is not satisfactory, and you fail to accommodate the inner transition metals, and some of the elements are not arranged in the continuous electronic configuration. For example, like copper and full shell, half shell kind of electronic configuration are not arranged. Okay, and these are the key trends which we are going to discuss along what happens when we move across the group and down the across the period and down the group. What happens to the important properties of elements. Now the importance of periodicity can be seen. So for alkali metals, lithium, sodium, potassium, rubidium, cesium and francium, the atomic number increase in the same group. The electron configuration, new shells are at 2s1, 3s1, outermost electron 4s1, 5s1, 6s1, 7s1. So this highlights the properties of these elements, similarity and number of shells, the new shell addition, outermost shell arrangement and so on. And we also look at the electronic configuration where by looking at the atomic number, element and the what are the electrons present in orbital can be arranged based on the electronic configuration. So what is the orbital? What is the number of electrons in that particular orbital can be understood from this electronic configurations. And what are the important aspects in operations based on this, and also importance of periodicity can be understood also based on these three fundamental parameters like Pauli's exclusion principle, where you cannot have no two electrons in an atom may have all set of four quantum numbers, and no orbital may have more than two electrons in a particular thing, and they are supposed to have with opposite spins. So, for example, we can have this orbital, okay, which can be having one orbital, so we can accommodate two electrons. P sub-level orbital, you can have three, and you can accommodate sub-level orbital, you can have five orbitals. Accommodate seven orbitals and 14 electrons. So this is how the orbitals and sub-level allows to determine what are the maximum number of electrons can be accommodated in the sub-levels. And the sequence of energy levels, how this is being filled, can be understood by Aufbau principle, where energy levels are filled and order of filling. So 1s, 2s, 2p, 3s, 3p, 4s accordingly can be understood from Aufbau principle. So these are the important properties. What exactly we mean by atomic size, ionic size, and what exactly is ionization energy, how much energy is needed to remove an electron from the atom of ion, and electron affinity, and how much of the energy is released when we add electron to the neutral state, and electronegativity, the attraction of electron towards itself. Yeah. So this is the first aspect, covalent radius. Covalent radius is generally the size of an atom. So you can see down the group the size decreases, across the period the size reduces. And we have given this in terms of picometers, and you can see here atomic radius across the period it decreases because we are adding we are adding electrons to the same valence shell. So what happens? The nuclear charge will be higher, and the valence shell is held closer. We need to also make it a point that in the understanding of periodic table, we need to have Aufbau principle, Pauli's exclusion principle, Hund's rule. All these things are very well taken care into account. And also, if you look at the atomic radius, it increases down the group. Okay, so you can see that lithium, sodium, potassium, rubidium, cesium. These are the alkali metals. When we add the new valence shell of electrons, they will be having the atomic shell, new shells are added, so the size or the atomic radius increases. And for the noble gases, you can see in the same period you have number of electrons added for the same shell. So the size for these are minimal, and all these are the radius is in picometers. So from lithium all the way to cesium, the size ranges from 150 picometer all the way to um, 290 picometers. So what are the general trends, especially group trends in atomic radius? So when the size of atom is related to the distance of the valence electrons from the nucleus, and the larger the orbital of an electron, the farther, the more distance it will be from the nucleus, so the attraction will be less from the nucleus. And if you move down the group, you are adding new energy shells. And the larger the principal energy, the larger its volume. Okay? So, and what happens? Quantum mechanics predicts what are the atoms. If you down the group, if you go, what happens to its atomic trends. And uh, we also can look at with respect to atomic trends, the larger the effective nuclear charge it experiences, the stronger is the attraction from the nucleus. So the stronger attraction, the valence electrons will be having a stronger attraction to the nucleus, and the distance will be closer. And if you are moving, the effective nuclear charge on the valence electron increases with effective nuclear charge. So quantum mechanics predict atomic periodicity of atomic radius across the period decreases. Important parameters in trends in ionic radius are ions in the same group have same charge. Ion when it decreases ionic size when it decreases down the column because you have higher valence shell and larger will be the size. So cations will be having smaller size than metal atoms. Anion will be having larger size. So these are the general pattern, and larger positive charge means smaller cation, larger negative charge means large. How would we define ionization energy? Is the minimum energy is needed to remove an electron from the atom or ionic state. We call it as ionization energy. So because the valence electrons which are away from the nucleus or valence electrons are easier to be removed, which means they will be having the lowest ionization energy. Always first ionization energy is energy that is needed to remove one electron from the neutral atom. Second ionization energy is energy which is needed to remove the electron from the ionized or already charged atom. So one important aspect about ionization energy is how much energy is needed to remove an electron from the outermost shell is called ionization energy. What are the general trends? So the how much effective nuclear charge is there? It is that difficult to remove the electron from the outermost shell. The more it is, the difficult. So the far the electron, the outermost shell. So the distance, the farther it is easy to remove the electron from the outermost shell. So what happens? What are the important points? Are the ionization energy it decreases down the group because you have valence electron far from the nucleus, and generally first ionization energy increases across the period because same shell we are adding electrons. So removing next electron from the already removed shell it is difficult because the effective nuclear charge will be larger. Whereas in the group new shells are added, so removal of the electrons will be easy. These are the first ionization trends across the around the group. So the highest ionization energies are observed for noble gases like helium, neon, argon, krypton, and xenon. And the alkali metals are the ones with the least ionization energies. So you can see that helium has almost close to 2400 kilojoule per mole, and followed by xenon close to 1300, whereas lithium all the way till rubidium, all those they lie in the range of less than 500 kilojoule per mole. And these are the trends of first ignition energy. So you can see that the ionization energy range values or energy ranges is in from 1312 kilojoule per mole. So, and for the helium, the first ionization energy across the same period, it is 2300. So, what we can understand from this is the first ionization energy for all the alkali metals are less, whereas if you move across the period, new shells, for the same shell, electrons are added, so the ionization energy increases, and the highest will be for noble metal elements. It means for first ionization, removal of one electron from the outermost electron. And what about the removal of ionization next electron from the same shell? So what happens? Already we have removed one electron, so the effective nuclear charge will be on the remaining electrons, and the same shell will be larger. So because of that, there is a shrinkage of size. Okay, because you have more number of protons than electrons, and outer electrons, they come close towards the nucleus, so it is very hard to remove. And the in energy because of excess continuous valence electrons removed, and the large energy is needed when you are coming closer towards the core or inner shells. It is difficult to remove. So this is one example. So here is an example for sodium and magnesium. In the case of sodium, removal of one electron, for example, 3s1 is very easier. So we can remove the first electron very easy from the outermost shell, whereas the next electron, which is attaining the neon configuration, we need to almost supply 10 times of energy, while once you remove the second electron, third electron, again it is going towards fluorine kind of electronic species and isoelectronic species. So the third energy, ionization energy, is close to 6,900 kilojoule per mole. So what is important is always the second ionization energy is larger than first. And in the same way, in the case of magnesium, the first electron you have 738 kilojoule per mole. In order to remove the second electron, which is easier to attain so that it attains neon configuration, and the third electron from nucleus you want to remove one more isoelectronic species to removal of an electron takes more energy, which is 7,730 kilojoule per mole. It is almost 10 times than first ionization potential. There are some of the trends for second and successive ionization energy. So you can see that removal of one electron is easier. When you move across to multiple core electrons, then removal of electrons will become extremely hard, and then where we are attaining the core electrons, and it is across the same period. We try to understand the exceptions in the first ionization energy trends. The first ionization energy trends generally increases from left to right across a period. There are exceptions for 2A, 3A, and 5A to 6A, for example. Beryllium and boron. So you can see that there is one extra electron there added with the 2p electron, and similarly in the case of nitrogen, we have half filled. So the ionization energy for the half filled is larger than as compared to oxygen. Likewise, if we look at exceptions in the beryllium and boron, in case of beryllium, you need to break up the first full sublevel, which you need to have higher energy, okay, in order to remove this particular electron. Whereas in the case of boron, it is very easier to remove because that one electron is excess, which costs less energy. Likewise, if you look at nitrogen, where we have half filled, so removing this electron will be having higher energy as compared to oxygen, where removal of one electron is less. Why the first ionization of aluminum is lower than magnesium? So magnesium, we know this electronic configuration. outermost shell is 3s2, and this is the aluminum electronic configuration. So aluminum has one unpaired electron in its highest energy orbital, whereas magnesium it is in the 3s orbital and it is paired. So what happens is, in order to have the electrons and orbitals to be paired, which means you want to break up the energy for the paired electron, and then so you need to have more energy magnesium than aluminum. That is the reason aluminum has lower first ionization energy as compared to magnesium. Electron affinity is the energy which is released for a neutral atom when it gains an electron in the gas state. So the more energy that is released, the larger will be the electron affinity. So the more negative, the larger will be the electron affinity. Depends in electron affinity. So alkali metals, they show decrease in electron affinity when down the column. Generally, there is irregular increase in electron affinity from second period to third period. Because you're having more negative if you move from left to right, because more number of electrons are being added. And again, it is not an absolute thing. So five-way electrons, five-way group will generally have a lower electron affinity, and because you're having extra electron pair, the pairing is there, and 2A and 8A generally will have lower electron affinity because you're having to higher energy subunit. Generally, highest electron affinity is mostly towards halogens. So you can see the electron affinities for typical uh, elements. Um, the highest will be in the case of chlorine, which is minus 349 kilojoule per mole, followed by chlorine. And one more aspect about electronegativity is how much the ability of an atom to attract electron towards itself. We refer it as electronegativity. And what happens when you move down the group? When you move down the group, electrons are far from the nucleus. So what happens? There will be weaker attraction, and across the period it increases because you are having core charge and then the greater attraction to the outer shell of electrons from the nucleus. So these are the important trends with respect to electronegativity. So you can see across the period it increases, down the group it decreases. And so with respect to Pauline's electronegativity, it is a very important factor where fluorine is the one which is most electronegative, which is close to 4, and francium is the one which is least electronegative, close to 0.7. So, and it is very important to understand the electronegativity difference between two or very atoms. When it is high, bonding type is more ionic. If the difference is small, then we call it as non-polar covalent bond. So these are some of the important points which are understood with respect to Pauline's electronegativity and the impact which it creates on the kind of bonding types, the difference. And we also have an interesting aspect with respect to metallic character. So as we already discussed, metallic character across the period decreases, and down the group it increases because we are adding new shells, outermost like new shells are being added, and we are having electrons more. And these are the summary for things in the periodic table. What we gave an overview with respect to shells, with respect to size, with respect to electronegativity, electron affinity, ionization energy, and metallic character, and so on. Shall address an important aspect about shielding. When we have a multi-electron system, how electrons are attracted toward the nucleus and are repelled by each other, we understand by means of shieldings. Generally, outermost electrons are shielded by nucleus by core electrons, which means the core electrons are not allowing the outermost electrons to experience the complete charge. The shielding causes the outermost electrons not to experience the full strength of the nuclear charge. So these are the core electrons. This is the outermost. So the inner or the in between shells electrons are not allowing the nucleus to outermost electrons to experience the exact nuclear charge. One important point is between electron there will be repulsions, and with the outermost electrons to the nucleus we have a attraction. So how do we define nuclear charge? It is a charge on the nucleus which attracts the electron in the atom. Basically, the nuclear charge is equal to atomic number. Generally, it is denoted by Z. What is shielding effect? Like multi-electron system, the orbitals when they are filled, the electrons in the inner orbitals shielding or masking the electrons of the outer orbitals is called shielding. And what exactly the outer orbitals will not experience the same force or charge on the nucleus. This decrease in the charge is referred as shielding effect. Shielding effect we define as the measure of extent to which intervening electrons shield the outer electrons from the nuclear charge. We refer it as S. So what exactly is effective nuclear charge? Is Z star, which actual charge felt by outermost electrons by taking care into shielding of electrons. So this is how effective nuclear charge can be articulated. The effective nuclear charge is a net positive charge for a particular electron, and atomic number is the or effective nuclear charge or nuclear charge, and S is the number of electrons. Shielding is the number of electrons in the lower energy levels. So these are the particular trends where it follows. And one important aspect is electrons in the same energy level contribute to the screening, and their contribution is very minimal during the calculation of the shielding constant. So these are the trends, and the effective nuclear charge can be calculated by taking atomic number minus shielding constant. So these are, for example, in the case of lithium, you have three um, positive charges and three electrons. The core electrons are two, and outermost are one. So what is the effective nuclear charge on um, lithium is? So three positive charges minus shielding constant, because these two are shielding the outermost. So 3 minus 2, 1. And one important aspect on how to calculate effective nuclear charge is stated by Slater's rule, where Slater proposed a set of empirical rules to understand the concept of effective nuclear charge to calculate shielding constant or shielding constant by using this formula, atomic number minus shielding constant. So how we can calculate shielding constant by using Slater's rule? There are important steps, like where the step 1 includes writing the electronic configuration using this design. All the 1s, 2s, 2p energy levels could be written in bracket, and 3d, 4d, even though 3d is in the same level. So we are separating d, 3p, and d into some sets, and we are arranging. And then I look at the electron of your interest and ignore the rest of the electrons, so that they do not shield with respect to the lower groups. So this is the important rule for step 3, where Slater rule is now broken down into two cases. The experience by S or P electron. Okay, so you can see that these are the inner or core electrons and this is outermost. So how much the shielding extent we can see. Electrons within the same group, they shield 0.35. Okay, they shield 0.35 except for 1s. For example, helium, like that, where they shield 0.3. Electrons, lower groups, they shield 0.1 in this one, and n minus 2 or lower, they shield 1. And if it is for S, these instances are for S or P electron, shielding experienced by D or F electrons, in the same group they shield 0.35, and the lower groups they shield 1 for D or F electrons. Now, how to calculate the shielding constant for a valence electron of fluorine? So write the electron configuration of fluorine, and then group it into Slater's rule like 1s, 2s and 2p. And here second rule doesn't apply because there are no extra electrons where you need to find out the effective nuclear charge. Now out of these 7 electrons, okay, there are 1 electron is our interest, so 6 into the same valence shell they contribute 6.35. So and remaining n minus 1, this is n minus, same group is n minus 1, they contribute 0.85. So how to calculate this? 0.85 into number of electrons in the same shell, 0.85 into number of electrons in n minus 1 shell. So there are 6 electrons in same shell and 2 electrons in the, so it is 3.8 if you the effective the shielding constant. And from this we can calculate for the valence electron the effective nuclear charge is 5.2. 9 atomic number, shielding constant 3.8, we get 5.2 for effective nuclear charge. But in the case of fluorine, we have seen for E electron, what happens in the shielding constant experiments with 3D electron for bromine. Here, this is the configuration for bromine and 4s, 4p5, but we are 4p5, we are interested in 3D electron. So we are ignoring the 4s2 and 4p. So when we group the, as per the Slater's rule, this is how we assign the configuration, and we are not interested in these electrons which are involved in shielding. Out of 10 electrons, 9 electrons will be involved in shielding, 1 electron is our interest. So we are ignoring the rest, 4s2 and 4p2. This will not contribute in the shielding. So, and we have 9 electrons in the same group which is shielding for 0.35 since it's a d electron. So the rule is different for a d or f. So 9 electrons which shields in the same group 0.35 and remaining 18 electrons in the same n minus 1 where they shield 1 for a d. So the effective shielding constant is 21.5 and the effective nuclear charge is 13.85 for the valence electron of 3d electron for bromine atom. Likewise, Slater's rule is very important to explain why cation is always smaller than neutral atom. For example, Li atom and lithium atom. So if you see the electronic configuration of lithium atom is 1s2 and 2s1. You can, based on the Slater rule, we can arrange 1s, 2s. So only 1 electron is there. So that is our interest. So we have 1 electron, so the total electron involved in the shielding will be 2 into 0.85, 1.7. So the effective nuclear charge is 1.3. In the case of Li plus ion, we have only 1s2. So 1s2, 1 electron is our interest. So 1 electron is in the interest and it is in 1s. So the shielding will be only for 0.3. So 1 electron into 0.3 and 3 minus 0.3, so 2.7. So effective nuclear charge of Li is 1.3 and Li plus is 2.7. So which says that effective nuclear charge of Li plus is more than Li. So the size of Li plus is smaller than Li atom. Again, why anion is always larger than neutral atom? So this is the case of chlorine atom. If you look at the chlorine atom, the electronic configuration is 3s2, 3p5 outermost. We can make into the form of groups 3s2, 3p5. And if you look at the chloride ion, out of 7 electrons, 6 electrons are in interest, 1 electron will be the shielding constant we need to calculate. So 6 into 0.85 n minus 1 0.85 and 2 into 1, so it is 10.9. And atomic number of chlorine is 17 minus shielding constant 10.9, which is 6.1 for chlorine atom. In the case of chloride ion, we have 1 electron rich is excess, so it will be 3p6. So we can assign based on this configuration, and shielding constant can be calculated. Out of 8 electrons, 7 electrons are of interest. 7 electrons, 7 into same group 0.35 and 8 into 0.85 and 2 into 1, which is 7.25. So the effective nuclear charge is 5.75. So 6.1 for chlorine atom, 5.75 for chloride ion, which shows that effective nuclear charge on chlorine atom is more than fluorine. So due to which Cl minus will have larger size than Cl atom. And we also can apply Slater's rule for 6s electron of gold. So this is how the electronic configuration of gold is, and we can make groups based on the Slater rule in this particular, as per the rule 1. So we need to look at 6s electron, what happens to the effective nuclear charge. So here rule 2 doesn't apply because there are no extra electrons of interest. And so the same and the two 6s electron, and this particular 5s things we have 18 electrons. So this electron is so this is involved in the not involved in the screening of shielding. So 0.85 into 18 and remaining 60 electrons into 1. So we have close to 75.3 for shielding constant, and from subtract from atomic number it is close to 3.7 for valence electron. So what are the important applications of Slater's rule? It provides a quantitative justification for the sequence of orbitals in energy level diagram, and it tells us why filling up of ns orbital as compared to n-1 d orbital. Okay? For example, we will take an example of potassium, which is atomic number 19, in which the last electrons enters into 4s orbital or 3d orbital. Let us see by applying Slater. So this is how Slater rule, the set of rules where we take into consideration s or p electron, same group 0.35 except 1s, and n-1 it is 0.85, and n-2 and so on 1. Case of D, it is same group 0.35 and 1. Let us assume the electron enters in 4s orbital than 3d orbital. If you look into account into the case of Slater rule, 4s1. Okay. So if you look at 4s1, so this 6 electron, this is the one interest. If we apply in the 4s1, there is no extra electron, so 0 into 0.35 and 8 electrons into 0.85 n-1 and 10 electrons into 0.1, which is 16.8, the shielding constant. The effective nuclear charge is close to 2.2 when the electron enters in 4s1. Whereas the assume that if the electron enters in the 3d orbital rather than 4s orbital, then the electronic configuration can be given like this: 3d1 d. If you apply the second part of the Slater rule, within and yeah, so 0.35 and then remaining thing it is 1. So 18 into 1 because 3d1 1 into there is no electron, 0 into 0.35, so it is the Slater rule is it is 18 shielding constant, and the effective nuclear charge is close to 1. So if you look at the effective nuclear charge, the greater the nuclear charge is seen for 4s electron Fasham entry as compared to 3d, due to which the 4s orbital will be more attracted to the nucleus and will have lower energy than 3d electron. So that is the reason why the last electron will enter the 3d orbital rather than the 4s orbital rather than 3d orbital of potassium atom. And there are a lot of other examples when which electron will be moved when zinc is ionized, whether it is 4s by applying this screening constant and Slater's rule. We can understand from this 3d electrons will experience greater positive charge than 4s electrons. So then, due to which 4s electrons will be removed first and they are ionized. The summary of periodic properties. In summary, we can see that how the shielding constant changes and how the atomic radius decreases if you move across the group, how ionization energy increases across the group, and electronegativity character increases across, and nuclear charge how it increases, and how we understand Slater's rule and how it can be used to understand the size of cations are smaller and anions are larger, and why the entry is for 4s as compared to 3D for potassium cases, and the ionization, all those aspects we can understand using this particular periodic knowledge NPTEL, and some of the chemistry books like Chemistry 3 for text and material making, along with some of the manuscripts and other sites where we have taken the material and made this presentation.